Modern vehicles and their complex driver assistance and safety functions are made possible thanks to the comprehensive integration of electronic control modules. These implementations require very high data transfer rates to transmit the increasing number of control and status signals. The signals not only need to be transmitted extremely quickly, their transmission also needs to be time critical. The popular use of steer, drive and brake-by-wire systems by manufacturers requires the design of fault-tolerant network architecture and associated hardware. This is the reason for the growing importance of communication systems that guarantee fast and time-critical data transmission. The control area network communication system cannot meet the needs of these new systems due to its limited bandwidth and event-driven bus signals. As only one message can be sent via CAN bus at a given time, priority coding must be applied to each message. The downside of this means, with an increasing number of control modules in today's vehicles, individual control area networks become saturated with data, requiring manufacturers to install as many as 5 of these networks to cope with the load. Unfortunately, data congestion causes the network to run slow and become unreliable. This means manufacturers cannot safely continue to use these networks to operate drive, steer and brake-by-wire systems. FlexRay is one answer to these heightened data transmission requirements. Many aspects of FlexRay are designed to keep costs down while delivering top performance in a rugged environment. FlexRay may use unshielded twisted pair cabling or optical fibre to connect nodes together. FlexRay supports single and dual channel configurations. Although, when configured as dual channel, increased bandwidth is attainable due to lower transmission error rates and data redundancy. Most first-generation FlexRay networks only use one channel to keep wiring costs down, but as applications increase in complexity and safety requirements, future networks will use both. Differential signalling on each pair of wires reduces the effects of interference on the network without expensive shielding. FlexRay buses require termination resistors just like controller area networks. Only the end nodes on the bus need this termination. Too much or too little resistance here can affect the network. While specific network implementations vary, typical FlexRay networks have a cabling impedance of between 80 and 110 ohms, so the end nodes are terminated to match this. Unwanted high-frequency noise is filtered from the FlexRay bus using split termination resistors. The filtering is accomplished with a coupling capacitor between the two series-connected termination resistors. FlexRay supports a simple daisy chain connection, an active star connection, or a combination of both for more complex network designs. Depending on the vehicle's layout and level of FlexRay usage, selecting the right topology helps designers optimise cost, performance and reliability for a given design. FlexRay is commonly used in a simple multi-drop or daisy chain bus topology that connects multiple ECUs together. This is the same topology used by CAN and LIN and is familiar to OEMs and technicians alike. Each node can branch a small distance from the hub of the bus. Again, the ends of the network have termination resistors installed to eliminate problems with signal interference. This type of topology also fits nicely with vehicle harnesses that commonly share a similar type of layout, simplifying installation and reducing wiring throughout the vehicle. Star configurations consist of individual links that connect to a central active node or hub. The active star configuration makes it possible to run FlexRay networks over longer distances, or to segment the network in such a way that makes it more reliable should a portion fail. If one of the branches of the star becomes compromised, the other nodes are able to function as normal. As the amount of wire cable used in a star network is reduced, environmental or electromagnetic interference is less likely to interfere with communication signals. Daisy chain and star topologies can be combined to form a hybrid network topology, taking advantage of lower production cost while applying the performance and reliability of a star network. Just like CAN, data communication in a FlexRay network is also based on a multi-master communication structure. However, unlike CAN, every node has an independent clock that is periodically synchronised to a reference or master. It's this clock synchronisation that allows the transmission of time-critical or deterministic data. FlexRay nodes are not allowed uncontrolled bus access in response to application-related events, as in the case with CAN. Rather, they must conform to a precisely defined communication cycle that allocates a specific time slot to each FlexRay message. An independent control mechanism known as the bus guardian ensures that a FlexRay node only gets access to the bus during its turn in the communication cycle. This prevents bus monopolisation by a defective FlexRay node. Each communication cycle is equal in length and is organised into static, dynamic and idle time segments. The static segment is used to transmit the messages between the nodes. It's subdivided into sections containing the timestamp, error correction bits, and any time-critical messages from the transmitting node. All static time slots are the same length. The order of the data sections is also permanently fixed. From one communication cycle to the next, the message contents may change, although the entire time slot structure is always transmitted regardless of whether all slots contain a message. The dynamic segment, which is also subdivided into sections, is received by all nodes. This segment is a reserved space within the communication cycle. This segment operates similar to CAN, allowing nodes to send and receive event-based data. This data must still adhere to the synchronised communication cycle. The network idle time will vary depending on the length of the dynamic segment. This ensures each communication cycle remains within the same allocated time frame. This is the time when no data is being transmitted over the FlexRay bus. Bus nodes may use the network idle time to synchronise their internal clocks with the reference or master clock. Traditional CAN protocol allowed for a maximum of only 8 bytes of data, whereas the FlexRay data packet may contain 256 bytes of useful data. In the FlexRay network, one bit of information has a width of only 100 nanoseconds, with the complete communication cycle lasting only 40 microseconds. CAN protocol is a binary network using ones and zeros for message transfer, whereas the FlexRay bus operates with 3 different bit states: idle, data 0 and data 1. The idle state is used to ensure the length of each communication cycle remains the same. The 2 electrical circuits of the FlexRay network are similar in function to CAN and designated bus positive and bus negative. Their voltage levels vary between 1.5 and 3.5 volts. At idle, both signal voltages sit at 2.5 volts. When the bus positive is low and the bus negative is high, the signal status is data 0. Likewise, when the bus positive is high and the bus negative is low, the status is data 1. The signal transmission is by means of differential voltage, just like CAN. The receiver node detects the actual bit status by the difference between the bus positive and bus negative voltage. If no activity takes place on the bus for a predetermined time, the FlexRay network automatically enters sleep mode. FlexRay data transmission is able to meet the demands of automotive systems with data transmission speeds of up to 10 megabits a second. This supersedes CAN, which has a top speed of about 0.5 megabits per second. FlexRay is just one of the global technologies technicians will be seeing more and more of. So keep training and don't get left behind. Thanks for watching.